Hello. Last lecture we developed a technique that is a hypothesis to test whether the mean vector is equal to a particular vector. Naturally, we would like to compare two or more vectors. That is what we are going to do now. So starting with the generalization of paired comparison, where we have two treatments, computing the Hotelling t-square statistics, where we use differences, then computing the value of the Hotelling t-square statistic without computing the differences, introducing the confidence intervals, so simultaneous and Bonferroni confidence intervals, and for the paired comparison, in the end we will use more than two treatments, so we will use Q treatments. And in the end, we will compare mean vectors of two independent populations. There is also a generalization of ANOVA models, which are called MANOVA, so multivariate analysis of variance. That is what we're not going to do in this lecture. Let's go to paired comparison. So assume that we have two or more treatments. Those treatments can be measured on the same or similar experimental unit. And then we want to compare the effect of that treatment on those units. For example, it can be a testing of a drug. So we can measure before using the drug and after using the drug, and then we can compare to see if the drug had some effect on the units, experimental units, in this case people, or a group of people. So even though we have two treatments in our first case, we can have more variables. So I here will represent the number of variables that we have, and we can, for example, have 5, so p variables. Later we will generalize to more than two treatments. So what we want to do is assign both of those treatments that we have to the same unit, and then pair those two responses, compute their differences, and in that way we eliminate much of the influence of the variation. So in univariate case, we had response to treatment 1 and response to treatment 2 for each of the trials. Then we pair each trials and compute their differences. The notation was a little bit different than what you see on the screen. So instead of x1 yot I, because we had only one response there in the univariate case, we had only x, for example, yot 1 and x yot 2. And then we just compute differences, x yot 1 minus x yot 2 for each yot, so for each observation or trial or unit. So for each pair, we compute the difference. Then we used t-statistic, a statistic that has students t-distribution with n-1 degrees of freedom, where we tested that delta, hopefully you will see it on the screen somewhere, is equal to 0 against alternative that delta is different than 0. Where that delta is by assumption mean of our differences. So here we assume that our differences follow normal distribution with mean delta and some variance. So let's now generalize that case for more than two variables. So when we have p variables. Now we need to introduce one more subscript here in order to see for what variable and what treatment are actually the observations. So first notation is going to represent the treatment. So for example, this is treatment 1, this is treatment 2. Second subscript, yot, is going to be from 1 to n, and those are the trials or observations. And the third subscript will represent the variable. So variable 1, 2, 3, or p. So basically, For example, if we have 1, 1, we have that this is variable 1 under treatment 1, if we have 1 here. In that sense, we can now compute the differences. So what we want is x yacht 1 yacht 1 to compare with x2 yacht 1. So this is our goal. This is equivalent to what we had for the univariate case, that x yacht 1 minus x yacht 2. So that difference. We will denote that difference as d yacht I. So this is, for example, d yacht 1 is when you just substitute for the first variable. So basically we just add the third subscript that represents the variable. And in that way we obtain all the differences. Then we put those differences in a vector. Okay, so d yacht is going to be our vector, where each element is actually difference for the first, second, or pth variable. Okay, so this is equivalent to our n. So because we have n those differences, instead of in univariate case we had n values, so n numbers. Now we have n vectors. So for each yacht we have different vector, and yacht are the trials. So for each trial we have different vector. In univariate case, we assume that it follows, so the differences, univariate differences, follow normal distribution with mean sigma and some variance. Here, we will assume that the differences, so our vectors now, are actually coming from a multivariate normal, p-dimensional, okay, random, so it follows that distribution. So they are actually random vectors with normal, multivariate normal distribution, where we now have some delta that is going to be our mean vector and our covariance matrix. So we will denote it with sigma d. Based on what we have proved or mentioned earlier, we know that we can use a particular test statistic to compute our values in case when null hypothesis is that the mean vector is 0, then the Hotelling t-square statistic is going to look like this. And we already know the distribution of this test statistic. We can also generalize it, where instead of delta is equal to 0 vector, where we have some other vector. This is basically the same procedure as we had in previous lecture, but instead we first need to compute the differences and to pair the corresponding units for each treatment. So these null hypotheses actually mean that there are no average differences between the two treatments. So this is why we are interested in zero vector. Another way to compute this Hotelling t-squared value is to use contrast matrices, where all rows are orthogonal to the unity vector. So if we have a contrast matrix C with a vector which is a row vector, C1 transpose for example, then C1 transposed and bold 1 is going to be equal to 0. So their dot product or color product is going to be 1, and sum of all elements of each row is 0. So this is our contrast matrix. We already mentioned that, just quickly. So using a particular C, which satisfies this assumption, we can actually see that the differences can be computed in this way. Also, SD can be computed like this. By substituting these two values in our Hotelling t-squared statistic, we can compute the t-squared value without compromising or computing the differences. However, that might not be a good idea if we don't know that the differences are normally distributed. So we would like in general to compute the differences so we can check the normality in practical cases. You would naturally ask what are the average here, or our matrices, for example SD or SX in this case. Well, now because we have more treatments and more variables, say that we have p variables, then this vector x is actually going to be 2p times 1. So this vector is going to be a column that has 2p elements. So this is here. And this Sx is going to be a matrix that is 2p times 2p. So we have 2p rows and 2p columns. It is going to be more clear on an example. Then the simultaneous and Bonferroni intervals can be computed in the same way as what we explained in the previous lecture. And in the end, for the paired comparison, we have, when we have q, so q different treatments, then we can use this procedure, this test procedure, where we actually have a little bit different test statistic and a little bit different Fisher distribution that can be proven, where we choose this matrix in a particular way. So this is going to be much more clearer on example. We will talk about this a little bit later. So let's go to an example. Okay, say that we have this data, so the treatments from lab 1 and laboratory 2, where we have these variables, so 1 and the second one. We have two variables and two treatments. So our I, so our first subscript can take values 1 or 2. Our second subscript can take 11 values. And because we have two variables, so we have 1 and the second variable. And let's test hypothesis and compute Bonferroni and simultaneous intervals. To do that, we need the differences, then the covariance matrix of the differences, the inverse, and in the end we can just use the test statistic and compute the value of the test statistic as we previously did. So what we first need are the differences. So we need this one minus this one. So for the first variable, both treatments. Then for the second one. So those are our differences. So this would be d(1) and d(2). Okay, then what we need is our mean vector, so average, and of this one as well. So this is our d bar transposed. So this is d bar transposed. Then what we need is our matrix, so covariance matrix. So what we said is that we can compute it directly. So we know that it is 2 times 2. So we need to matrix manipulate this one minus 1 transposed. Then this one minus 1. Okay, so basically what we have done so far many times, times 11 minus 1. Control Shift Enter. Not times, divided by. You can always see that you have made a mistake when you see larger numbers. So it needs to be divided. Then we need inverse of this, but we can compute it directly. The value of the test statistic. We do not need to compute the inverse separately. So this is our, let's call it as p. The value of the test statistic is one quality multiply matrix multiply. So what we need is first our vector, this one. Then we need the inverse. So inverse of this one. And in the end, our transposed okay. And then times n, because this is our t squared. Okay, so we have t squared, and under null hypothesis we know the distribution of n of t squared, or we can multiply t squared with a constant and then we know that it has Fisher distribution. So let's multiply this with the constant. So this is times 9. So because we have two variables, divided by 20, right? So we have n minus p, so 11 minus 2, n minus 1p, so n minus 1 is 10 times p, or maybe let's write it like times 11 minus 2 divided by 11 minus 1 times 2. This is so this is our constant times our t squared, and we know that it has Fisher distribution with p and n minus p degrees of freedom. So we need to compare it with our Fisher inverse of, let's say, 0.05 significance level, and degrees of freedom are p, so 2, and n minus p, so 11 minus 2. We get 4.2 something, and the value of the test statistic is larger, so we reject null hypothesis in this case, which means that there is a significant difference between the treatments because we rejected the null hypothesis. Okay, we also said that we want to find simultaneous confidence intervals. So for that we need our constant c. So c is going to be square root of, so we had p times, so 2 times n minus 1 divided by 11 minus 2, okay, times our Fisher. So this is our constant c. This is for simultaneous. We also need square roots, so square root of SIDII, so of our SD, divided by 11, and square root of this one divided by 11. Okay, now we can compute the simultaneous confidence intervals. For Bonferroni, we would need the value of the test statistic. So to avoid complicated computations, we can use matrix multiplication. So when we multiply this vector, so this is our vector of means transposed, minus, so we would need our constant c multiplied with this vector. Okay, so in that case we will get a vector 2 times 1, and each has, so our average minus constant times this. So this minus this times this, and in the end this minus this times this. So this is how we can get it at once. Okay, and for the second one, we can do the same. So what we need is the same, but with plus. Let's see if we copy this. Everything. And type plus. We need to, I misclick, so just okay, but we said plus. So this is what we get. So those are our simultaneous intervals. Let's compute Bonferroni, and then we will mention what happens. We need our t-value for the same 0.05, but because they're Bonferroni, because we have two variables, we would need to divide our alpha. So if our alpha is 0.05 and we have two variables, we need 2 times 2. Okay, so we need this divided by this in order to get the Bonferroni intervals. So alpha divided by 2p, right? And then we need our inverse. So and n minus 1, so 10. So we get 3.04. Okay, so Bonferroni. Okay, we need the same. So this minus, but instead of multiplying with constant c, we will multiply it. Okay, so it of these degrees of freedom and okay, those minus times and the same here plus constant. Okay, so let's analyze what happens here. As we expected, Bonferroni are narrower than our simultaneous intervals, but the problem here occurs when we see that actually 0 belongs to the intervals, so to Bonferroni or simultaneous interval. But what is we here rejected null hypothesis, and we said that there is a significant difference between the treatments. So the simultaneous and Bonferroni intervals are for any value of a. So here we just chose 1a. Okay, so one particular choice of a. The a from the previous lecture. So where we have 1 on the ith place. So for any choice of a, the simultaneous interval should contain 0 in order for us not to reject the null hypothesis. So this is just one of our cases. But if for any a, so for any choice of a, we have that the simultaneous intervals contains 0, then we cannot reject null hypothesis. But in this case, we have only for this particular a's. So for particular a, we have that it contains 0. But in general, for any a, there are going to be some intervals that do not contain 0. So again, if all simultaneous intervals for any choice of A contain 0, then we cannot reject null hypothesis. But in this case, as we see, we rejected null hypothesis, so that is not the case. So in that sense, we can say that the differences are not significant. Only in that case, when all intervals contain 0, we can say that. Let's solve the same exercise but using the contrast matrix. So our C, let's move it here. So how does it look? Well, we know already that it is a contrast matrix, so it has sum of all rows 0. We know that it is orthogonal with 1. Actually, by the theory, we know exactly how it looks. So we need -1, 0, 0, -1. So this is our contrast matrix. In general, so it is 2 times 4, so 2 times 2p in this case. Then what we need is our x bar transposed, and we now need our s. Okay, let's first find x bar. X bar is our 2p times 1 vector, and it has average of all of the variables. So we have averages. Then we need to compute Sx. So to compute it, we need the covariance matrices of each. So we need S11, S12, S21, and S22. To compute them at once, not one by one, we need the differences. So we need this one minus this one. That way, when we compute the value, so let's first, we need to fix. So we are now fixing the means. We need 11. Okay. This is our matrix that contains each value, so mean minus our value. Okay, actually we need the opposite. So we need this. In the end, it would not matter, but yeah, in general, that's how we did it earlier. So what we have is 4 times 4 matrix, what we need. When we compute it the same way as we did earlier, we will actually get our Sx, because we need that one. So what we need is transpose of this matrix times this matrix. Okay, and then divided by n minus 1. So this is our matrix. We usually computed this minus the mean, but because it's paired, in the end we get the same result. You can check. So this is our Sx, let's call it. This is our R transpose, our C. Okay, what we need is our vector x bar transposed C transposed. So x bar, this is something that we already have, and then we need to transpose our C. Okay, that should be that. We need this but transposed, so this is the end of the formula. Next, what we need is our inverse of C S6 C transposed. So we need matrix inverse, and we have 3 matrices, so we need at least 2 matrix multiplication. So matrix multiplication of the first one, so our C, then our Sx, everything, we close, and in the end transpose of C, close for transpose, close for matrix multiplication, and close for inverse. This is our middle term, our inverse, and now we can compute t squared. So our t squared would be what we have here is matrix multiplication. So we are multiplying three matrices, matrix multiplication of our vector. So x transposed c transposed, then our inverse, our vector, and times, so we need n, it is 11. So we got our value of t squared statistic using this way. So let's compare it, 13, 13, okay, so we got correct answer. So this is a way to use this method. So just a quick summary, what we have assumed here is that our differences have normal distribution. In practical, you would like to check that, but based on the data that is chosen, we will just assume that. And in this way, we had no chance to find the differences and check their normality. So this is a little bit trickier than this one straightforward example. Let's see how we can use this matrix of contrast on another example. Say that we are given x bar and our sx on units, for example, n is equal to 40. So we have 40 units and we have three different factors. And we want to check pairwise, are the means equal? Okay, let's go to nodes for a second. We want to use this part. So we want these simultaneous intervals, we want to use this test statistic, and this so alternative that C mu equal to 0 against C mu is not equal to 0. The choice of this matrix, contrast matrix, can be one of many. So we can choose this C to be almost anything that satisfy the assumptions of the contrast matrix. But the most common two that are used are, let's go to Excel. So Excel, okay. The most common are C1 that has 1, 1, minus 1, 0, 0, minus 1, or C2 that has 1, minus 1, then 0, minus 1, 1, minus 1, etc. So if you would have more, you would go like this, so 1, minus 1, etc. Depending on how many you have. We have only this, so either choice of those two matrices, you can see theory to back this up a little bit, can be chosen to compute the value of the test statistic t squared using the formula that we already have. So let's see, will it differ if we use this matrix or this matrix? Okay, so this is our contrast matrix. Now we need to do the same what we did earlier, but in this case we have q is equal to 3, so 3 treatments, but only one variable, that is just for simplicity, so we don't have problems. So what we want to do is multiply our C1, okay, with our x bar. So this is our vector, not transpose. This is our transpose. Okay, and we also need the inverse. So it is going to be 2 times 2, Again, you need to see how many matrices you multiply. You multiply 3. So matrix inverse of matrix multiplication. So what are we multiplying? Is C, so in our case C1, then our S, okay, and in the end transpose of C1. Basically what we just did, the same. This seems correct. And now we need to compute our test statistic value. Okay, so the test statistic value is just multiplication of our three matrices that we already have. So first one is going to be our column vector, our inverse, and then in the end our, row and now column. So column is last. Okay, we need to multiply it. We said we have n equal to 40 here. Okay, let's see what happens if we do the same, but for our C2. So we just need to move a little bit values. It's basically the same. As we can see, we got the same value using this or this method. What I meant that the choice can be like multiple. For example, you can put 2, 2, minus 2, 2. You would again get the same result. So in the end, it does not matter. But if you choose those choices, then you get for sure the correct answer. So what are actually these? When you multiply, you will actually get the differences. So mu1 minus mu2, mu1 minus mu3, etc. As well as here, you would get the pairwise differences. So in the end, you get all the differences that you need. So either this choice, which is, I think, more natural, or this choice. But you still get all the differences. So mu1, mu2, mu1, mu3, mu1, mu4, etc. And here, mu1, mu2, mu2, mu3, but in the end you get the same. If you write it correct. So what differs here is the distribution of the test statistic. So our constant here is something else. So what we need is our q, so n minus q plus 1. So this is going to be n, so 40 minus q plus 1, right? Divided by 40 minus 1 and 3 minus 1. And in the end, okay, we need brackets. We need to multiply it with our value. So you get 44.08. So that constant is not the same as previously, because this statistic now has different distribution. And we need to compare this with Fisher. So right L, okay, probability, let's say 0.05, and degrees of freedom q minus 1, 3 minus 1, 2, and degrees of freedom n minus q plus 1, like this, n minus q minus 1. So we get 3.29. Okay, so we can make conclusion based on comparing of those two values. So in this case, we reject null hypothesis and we say that there is a significant difference between, because this value is larger. Okay, let's go to Simultaneous. confidence intervals. What we need here is our Fisher distribution. So what we need here is first, so probability 0.5, degrees of freedom q minus 1, so 2, and n minus q plus 1 for minus, okay, so this is actually the same as we got here. Yeah, actually here is, okay, so this is what we need. Okay, let's go to the notes for a second. So we have, okay, so there, here, the constant is not actually p n minus 1 n minus p, but instead we need to use n minus q plus 1 n minus 1 q minus 1. So I will correct this. So what we need is n minus 1 q minus 1. So 40 minus 1 times 3 minus 1 divided by n minus q plus 1. So this is our constant, and in the end we need to multiply with this. The covariance structure is something that we already know. It is given in the formula, right? So what we need is square root of, so square root of first one plus second one minus, actually second one is here, 2 times this one, and close. So this is one of our covariance structures. S11, S12, S22, and then we need to divide it by n. So this is our number. Then we need for, so this is for 1 and 2. We need for 2 and 3 and for 1 and 3. So for 1 and 2, 1 and 3 is similar. So S11, S13, S33 divided by 40. And in the end, S11, S22, S23, S33 divided by 40. Yes. So those are our numbers. So 40 divided by 40, but in the brackets. Oh, again, there is a mistake. We need to divide everything by 4. So it should be like this. Okay. And in the end, we can compute the differences. So we have that constant, we have everything. So what are our, for mu1 minus mu2, so this one will be mu1 minus 3, and mu2 mu3. Let's move it here. So we have our difference of the means. This is first what we need. So difference is this one, this one. So mu1 minus mu2 minus, we can even fix those two, minus, then we have constants, so square root this one. If we fix them, because we need just the same, but with plus here. Okay. So this is for the first difference. Second is 1 and 3, so we just need those. And 2 and 3. And here we need the same, but with this. So using this, we can actually conclude that 0 does not belong to this simultaneous interval. So in the end, we can conclude the same as we did here. We should reject null hypothesis. Let's go to next example, where we have 4 different treatments. So we will treat each of those as a treatment, and we want to test the null hypothesis, so the equality of the means, using the same procedure that we did just now. Just now we have 4 treatments, we have 30 trials. Okay, so first what we need is the difference between each value with its mean in order to compute our Sx. So we need first averages. Okay, so x bar transposed. Then we need 30. Okay, so our 30 differences. So we can just select everything. So those are our differences. And we now, using those differences, we can compute our matrix Sx. So the same way that we always do it, but now we need to see that it is 4 times 4 matrix. So we need to multiply transposed, okay, transposed, and this matrix divided by 30 minus 1. So this is our matrix. We need our matrix of contrast. So we will now use, for example, the first one. So 3 minus 1. It should be 3. Okay. So what we have is matrix 3 times 4. Okay, so we are here missing. So this is our contrast matrix. And now we just compute everything one by one by the formula. We need this transposed. We already have that one. So we can just start by finding first vector 3 times 3. So it is going to be our matrix C. So C, because I selected columns, so we need to compute C times our vector. Then we need inverse of our 3 times 3 matrix, and that 3 times 3 matrix is so matrix inverse we are multiplying three matrices. When we multiply three, we need two matrix multiplications. So okay, first is going to be our C. Then it is going to be our S, our transposed C. This is just by formula. And then, yeah, that should be it. So this is our inverse. This is our matrix. Okay, we also need this transposed. Okay, write it here. So T squared is going to be, we're multiplying three matrices. So our transposed, so this is X bar transpose C transposed, first one. Then we have our matrix inverse, right? And in the end we have again this one, but as a vector, and times 30, n is 30. So this is what we get. Then we need our constant times our value. So it is going to be n minus q plus 1 divided by, so n minus 1 times q minus 1. So this is our constant, n minus 1 q minus 1, and just multiply those two values. Okay, so this would be our value f, and our critical value is going to be, so Fisher inverse right tail 0.05, let's say. You will always have this significance level specified in the text. If it's not specified, you can always use 0.05. Degrees of freedom, we need to use another one. So q minus 1, n minus q plus 1. So 4 minus 1, 30 minus 1 plus 1. Okay, so this is our number. And we need to compare those two, as obvious this is much larger than this. So we reject null hypothesis, that there is no effect. Okay, so we can see that there is effect in the treatment. Even though it looks easy here, if you would need to compute it by hand, it can be tricky and complicated, especially because you need inverse of matrix and everything. So practice. You're never going to have on a test like 30 observations or a lot of treatments, or if you have, you're going to be given the most of the values that you need to compute the value of the test. But the procedure should be just explained. So again, how do we choose this matrix of contrast? So basically, this row represents mu1 minus mu2. This one represents mu2 minus mu3. So this is not random matrix. Okay, so this is it for this example. The following problem is going to tell us how the choice of this matrix can affect our results and how can we actually use it to conclude something else than the difference in the means. So before going to this following problem, you should refer to the example from the book. So read example 6.2 and then come back to this exercise. So here, instead of the difference between means, we are interested in some linear combination of those means. Particular, in this exercise, we are interested, for example, in sum of third and fourth, okay, minus the sum of the first and second. So you can see the description what that could represent in particular problem. So depending on what you actually need, you can choose and test it yourself. So now, because we are interested in the sum of third and fourth means minus the sum of first and second, we need to create the matrix C accordingly to that. So that would be just the first row. So those two come with plus. So we would have 1 and 1. They do not have a constant in front of them, so 1, 1. Then the first two we want with minus sign, so we will just put it with minus. Then what we are interested is in the sum of first and third, and the difference, so minus second and fourth one. So this is that linear combination. And the last one of interest is the sum of mu1 and mu4, okay, minus, so second one and third one. Right, so this is a way to create a contrast matrix. So using that and our procedure, as well as simultaneous intervals, we can draw conclusions. In general, depending on what you need, you can always create your own test. So depending on what you want to find out from the data. So the scientist here wanted to see the effect on a dog from those 4 treatments and their combinations in this case. Now that we know our matrix C, first when we know what we actually want to test, then it is easy to compute the value of test statistic and test whether this is true or not, and to see, using simultaneous intervals, which of those combinations affect or do not affect our conclusion. Let's compute it just to see how it works in Excel. So basically what we have done so far, the same. What we need is our averages. So if you already know what to do and do not want to practice, you can always move on to the next problem. So we already did that for 3 treatments, but we will do it again anyway. So what we need here are S. So it is going to be our, or let's go directly. So instead we will just go and compute our S 4 by 4. So we have our matrix multiplication of our transposed differences, okay, and our normal. This is our divided by, so this is our matrix. Okay, we have our C. Then we can even compute the value of the test statistic now immediately, without waiting, without computing everything. So but it can be a little bit confusing because we need, okay, let's compute matrix multiplication. So we want Cx. So Cx would be 3 times 1, right? So C x transpose transpose 3 transpose, because it is transpose of transpose. Okay. Then we need our inverse multiplication of our, so C times 1, then transposed uh, so it looks like there is a mistake. See, no, it's actually correct. and in the end we can compute the t-squared statistic. So volumetric multiply of our post, then we have our and in the end don't forget to multiply it by, and what we also need is our constant, right? So it is going to be this guy times the constant. So 19 minus 4 plus 1 divided by 18, 3, okay? And our Fisher inverse right tail, let's go 0.05 or minus 1, and 19 minus 4 plus 1. So what we can conclude is to reject the null hypothesis. So we know that there is an effect, right? To see which of those combinations affected our conclusion, we will compute our confidence intervals. So first we would need our constant C. So our constant C would be square root of 18 times 3 divided by 16, then times our Fisher. This is Fisher. Okay, so basically minus 1, 4 minus 1, or like minus 2 minus 1, right? Minus 1, minus 1. Then what we have is n minus q plus 1. So n minus q plus 1. Okay, so not 1 minus 1, but 4 minus. This is our constant for the interval. For the interval, we also need our square root of this divided by n. So we need this for each. But of this one, right? But we need the square root of this man. So this is our uh, actually we need first to compute. This is why this is not good to go the fast way, because we need our C Sx C transposed, because in this case this will determine the covariance structure. So what we actually need. So this would represent our value. So E1 transpose is SE1. So C1. This one. Okay, so let's go. What we need is C, so metrification matrix C, then S and transposed C. Okay. So now we have the covariance structure. So now we need square root of this divided by n. Okay. So we need all corresponding structures. So this guy here in the middle will be actually our covariance structure that we need. So this guy here. This is how you compute them. And just to be faster, okay, so we can just compute it now. So what we need, because we have the constant, let's go here. Okay, I never spell it correctly, but So what we need is our vector, so means. Those are what are we interested in. So those represent this combination, right? Uh, this is our difference that we're looking into. So for the lower, we need minus our constant times this guy here. Similarly, but with plus this time. So this is our upper limit. So for the first combination, second and third, what we can see that the first two do not contain zero, so they are the reason why we rejected null hypothesis. Okay, but the third one, we see that it contains zero, so we can conclude that this might be true. So there is effect for the first two, but for the third one there is no effect. And the last two problems concerning our comparing mean vectors from two independent populations. Okay, so this case we need actually three assumptions. Okay, previously we just assumed that the differences are normally distributed. Okay, here we need assumptions such as that population first and second, so the samples, random samples taken from those populations needs to be independent, so this sample is independent from this sample. This sample comes from, so it is a size of n1 and has mean mu1 and covariance matrix sigma 1, and the other one has mu2 and covariance matrix sigma 2. And here we will assume that they are equal, so that the covariance structures are equal, and that the both come from multivariate normal distribution. So both come from n multivariate normal distribution with same covariance structure. Then we can develop a test statistic similar to the one in univariate case, where we had S pool, which is given by this formula, where S pool is given by this. So it is the same as in univariate case when you first look at it. So this is just nice generalization. That. And this test statistic times this constant has Fisher distribution with p n1 plus n2 minus p minus 1 degrees of freedom. Okay, so this is nice way to find and test the difference of the two vectors. Obviously, there are more ways to do that, like MANOVA or similar, that we're not covering in this course. If you're interested, you can look up. Also, there is way to check if the covariance structures are equal. There are test statistics for such, which are we also not covering in this lecture or in this class in general. So we'll just compare means with when we have this assumption. So basically, when we have that those two follow some normal multivariate normal distribution with different means but same covariance structure, okay, then we can use this test procedure, and in that case, under null hypothesis, we know the distribution of this guy over. Okay, let's go to an example. So let's say that we have this data given here, where in first random sample is of size 45, and the second one is size 55, and we want to compare the means of those two, assuming that the covariance matrices are equal, okay, and we assume the normality of those two distributions. However, we have given, so here is x1 bar, x2 bar, s1 and s2. So these things are given. and we just want to use the test statistic that we just introduced, so as pooled. Okay, so we are testing if the means are equal, so we naturally need the difference between those two, and we also need the transposed. So we will need that later to compute the p-square statistic. Then we need S pool. So in this case, this is going to be our matrix, 2 times 2, right? What we need is, so we have n1 minus 1 divided by n1 plus n2 2, then everything times this matrix. Okay, so this is our S1. Similarly, what we need is now n2 times 1. Then we have this guy here, but divided with, and times the matrix S2. So this is our S pool. Okay, next what we need is inverse of, so we need matrix inverse of, let's open 1 divided by n1 plus 1 divided by n2, okay, times our matrix S pool. So this is another one. And in the end, we just compute the value of test statistic, compute the critical value, and compare the result. So our test statistic will be, we are multiplying 3 matrices, so 2 times this guy times guy and vector of difference. And we get value of the test statistic, 16.0. We need to multiply it with constant, so this guy times, we have 45 plus 45 plus, let's 55 minus, so p minus 1 was it, yeah, so p minus 1, so it is total of 3 divided by, so now we have this but times p, so because we multiply with p, 2 brackets, n1, hopefully I'm not mistaken, times 2. We need to close the brackets, multiplied, okay, so this is another, and in the end we need, because we know that it has Fisher distribution, so we need inverse of Fisher, p 0.05 degrees of freedom 2, and 55 plus 45 minus 2 minus, and when we compare it's larger and we reject null hypothesis, and we can see that there is significant difference between those two. And for the last problem today, we will have two populations, so for men and women, and we want to see if those variables differ. So what we need to compute the value is the average of each of those. So you can, for example, think that of The first is length of a shoe, then like width or something, and height. And we want to compare those two. So length, width, and height. Or how to go. So we want to compare those between men and women. We have averages, then we need so x1 bar, it is going to be transposed this one, x2 bar going to be transposed this one, transposed of this one. Then we need our S1, so this is 3 times 3 matrix. We will just compute it the fast way. So matrix multiplication of transpose. So this is S1. Don't forget that this can be also computed by hand. Divided by 23 in this case, because 24 is third, so 4, 2, and S2 for this one, the same matrix multiplication. Uh, Next time when we compute those matrices, I will just skip the computation, so that part is not going to be in the video. This is the last time that I show this part, just so you know. Then we need spool. You can always fast forward if you know what are you doing, but if you want to listen, leave it like this. So we need here spool is S1 plus S2, but we need divided by 2. So this is our. Okay, so I divided by 2 because we have the same sample size, but here I actually forgot to divide with 24. So again, divide by 2 because the sample size is the same. Then what we need is 1 divided by n1, so inverse of matrix inverse of our matrix. So 1 divided by, so it is going to be, because the sample size is the same, 1 divided by n1 plus 1 divided by n2. So this is just 12, right? Then you calculate it, it's half. Again, because the sample size is the same, always look at the formula times this. Okay, I didn't bracket. So this is our inverse matrix, and it is easy to compute now the value of the test statistic. So t squared is matrix multiplication, transposed. Okay, so first we would need the difference, which it is better to compute perhaps this one. Okay, now b squared because we needed the difference. What we have is matrix multiplication of now transposed, then there is our ring, and we have this. Okay, so transposed. So I added too many brackets, wrong places. So we get this value for our critical value. We just need to, because we have the same sample size, but let's write it by hand, multiply it with a constant, per 1 divided by 22 times 3. Okay, so this is our constant. I write some 24 or yeah, here 3 minus. Okay, and the critical value, which is probably around 3, is Fisher distribution 0.5. Then we need 3 for so 2.81. Let's just check the degrees of freedom again. So degrees of freedom, 3 variables, 1 plus and 2 minus 3 minus 1, so 48. So we see that this is larger, so we reject the null. You can always go further and find the simultaneous confidence intervals or the regions, for example, by finding eigenvalues and similar, but we are not going to do that. We already did that earlier, so it is going to be the same. So this is going to be it for the comparison, but keep in mind that there is much more to it than this. So thank you and see you next time. Bye.